Hello, this is MEI Further Maths Core Pure. We're in the third Matrices section and on the fifth and final video on inverses and transformations. You can watch the video straight through, but you will probably find it helpful sometimes to pause the video and try things out for yourself before continuing to watch. We've already seen that multiplying by a 2 by 2 matrix is a linear transformation. Multiplying by the inverse of this 2 by 2 matrix can be thought of as reversing the effect of or undoing this transformation. Here's an example. A point P is mapped to the point Q 4 minus 2 using the transformation represented by the matrix A. We're asked to find the coordinates of P, the starting point. So what we've got is that the matrix A multiplied by the point P, which we'll call xy, is equal to the point Q 4 minus 2. Pre-multiplying both sides by the inverse matrix gives us A inverse A xy equals A inverse 4 minus 2. Now we know that A inverse multiplied by A is the identity matrix, and that doesn't change anything, and so we've got that xy is A inverse multiplied by 4 minus 2. So let's just see what A inverse is. The determinant is 6 take away minus 4, which is 10, so that's 1/10, multiplied by swap the elements on the leading diagonal, so that's 3 and 2, and change the signs of the other two elements, so that'll be 1 and minus 4, and multiply that by 4 minus 2. So that gives us 12 take away 2 is 10, and 1/10 of that is 1, and minus 16 add minus 4 is minus 20, and 1/10 of that is minus 2. So the point P is 1 minus 2. And you can check that if you multiply that point by the matrix 2, 4 minus 1, 3, you do get 4 minus 2. Okay, let's think about reflection matrices. How do you undo a reflection? Yes, you do the same reflection again. So we should find that these matrices are what is called self-inverse. The easiest way to check that is simply to multiply the matrix by itself. And you can see that we get 1, 0, 0, 1, which is the identity matrix. So yes, this matrix is self-inverse. If you try to find the inverse using the usual rule, you'd find you had the same matrix. The same thing happens with the reflection in the line y equals minus x. This matrix is also self-inverse. If I multiply it by itself, I get back to the identity matrix. Okay, what's the inverse of rotating 90 degrees about the origin anti-clockwise? Pause the video for a moment while you work out the inverse of this matrix and check it is what you're expecting. Okay, the inverse of this matrix is 1 over 0 take away minus 1. Swap the elements on the leading diagonal and swap the signs of the other two. So that's just 0 minus 1, 1, 0. And you can check that that is the matrix which will give you a rotation of 90 degrees clockwise about the origin. What about a rotation 180 degrees about the origin? This should be self-inverse, because if you apply that transformation twice, you'll get back to where you started. So let's check. Multiplying that matrix by itself does give you 1, 0, 0, 1, the identity matrix. What about an enlargement by scale factor k? Pause the video for a moment while you work out the inverse of this matrix and think about what the transformation should be. OK, the inverse of an enlargement by scale factor k should be an enlargement scale factor 1 over k. Let's check this. The inverse of this matrix is 1 over k squared minus 0. Swap the elements on the leading diagonal, they're both the same, and change the signs of the other two elements, they're both 0, and we get that. If we multiply through by 1 over k squared, we'll get 1 over k, 0, 0, 1 over k, which is an enlargement scale factor 1 over k, as expected. In an earlier video, we found that using the inverse of a matrix product could be found by using this identity. The inverse of the product AB is equal to the inverse of B multiplied by the inverse of A. This is what we expect. Let's think of it in terms of successive transformations. If we apply rotation followed by a reflection, so that in our example above the rotation is B and the reflection is A, then we need to undo the reflection first and then undo the rotation. And that works. The same ideas work in 3 dimensions. These are the 3D transformations that you need to know for AS further mathematics. Reflections in one of the planes, and rotations of multiples of 90 degrees about one of the axes. And the inverse of a 3D matrix also undoes the transformation associated with that matrix. Remember that for AS level, you only need to be able to find the inverses using a calculator. Here's the rotation matrix. It's a rotation of 90 degrees anti-clockwise about the z-axis. You can use a calculator to find that the inverse of this matrix is 0, minus 1, 0, 1, 0, 0, 0, 0, 1. You can check that that matrix does give you a 90 degrees clockwise rotation about the same axis. There are more notes on integral or in your textbook on inverses and transformations. That's the end of this short video and the end of this section.